Hello and welcome to Introduction to Electrodynamics lecture series. As we discussed, the differential calculus is very important part of electrodynamics, so as the integral calculus. So integral calculus, this subsection 1.3 3.1 is a line, surface, and volume integrals. So in this video, we are going to discuss only the line integrals. So a line integral is expressed as v dot dl, where integration is performed from a to b. V is vector function and dl is infinitesimal displacement vector. So we need a path to integrate this integral. It's a path from a to b, and say we have a function v and we want to integrate it from over a line, and that line is like from A to B. So this is the path of the integration. And if this path is a closed path, like you go from A to B and then come back at B, then we can express this as a closed line integral. P dot dl, and we put a circle on the integration saying it's a integration, closed line integral. So the common example of the line integral is the work done. W is equal to F dot D. So this is the familiar example where we use line integral to calculate the work done. Normally, the line integral is path dependent. So if we are choosing a path, then if we choose a different path, then the line integral will be different. But there are special cases where the integration is independent of path, only depends on the endpoints. And for the forces that follow this property, like if the path of integration is independent, just depends on endpoints. Such fields are forces are called the conservative forces. So this is very important part of the study to find which force is conservative and which is not. So we have an example where we are given v, the vector function y square x plus 2x into y plus 1 y, and we are asked to integrate this over this line x, y, and we have to ask it integrate with two different ways. So one is to integrate two different paths. One path is this one, which is 1, another part is 2, which is from point A is here and point B is here. So point A is given. A is 1, 1, 0. And B is also given and is 2, 2, 0. So we have to integrate over two different paths, and we have to find the closed loop integral. V dot 0. So first, if we consider path 1, then we can divide path 1 into two parts. The one part is going from here to here. So point 1 is 1, 1. Point 2 is 2, 2. And if we go from path 1, so we can divide this into two parts. The first part is say 1, and this is 2. So part 1 is we have y fixed, y is equal to 1, and x is going from x is from 1 to x is 2. And if we want integral, then we need v dot dl. So we have given v, so what will be the dl in this case? Dl in general will be dx plus dy, but for this specific case we have no change. As y is equal to 1, it will become dx x, and y is 1, so dy will become 0, and dl become dx x. So we have to take v dot dl. V dot dl will become v dot dl will become y square x dot dx x, and dot product with y will come 0 because we have dy component 0, and it will become y square dx, where y is 1, so it will become just dx. V dot dl is equal to dx, and we have to integrate v from 1 to 2, v dot dl dx, and as dx and dot is only, this whole thing is dx, so it 1 to 2 dx is equal to x, 2 minus 1 is 1. So after integration on 1 is the result is 1. Let's try 2. We are going up from 1 to 2. So y is varying, but x is fixed. X is equal to x on this line is 2. X is equal to 2, and y is from 1 is less than y is less than or equal to 2. So if we want to find dx is in this case will be 0, dy is not 0, so dl will become dy and v dot dl will become, we are given 2x into y plus 1 and dy. X is constant, x is equal to 2, so it will become 4 into y plus 1 dy. So if we take integral v dot dl, so it will become 4y plus 1 integral 1 to 2 dy. And after performing the integration, 4 y squared by 2 plus y, and it goes from 1 to 2, and plugging in the values we will have 10. So on the second path, so we have 10. So if we want a to b, v dot dl is from a to x or any arbitrary value, which was v dot dl plus x to b v dot dl. So the first part is 1 and second is 10, so total integration is 11. So this number turned out to be 11. All right, so we have part 2. In part 2 we have to perform integration from b to a or b. Let me see, is a to b or b to a. So this is again we can do either way. We can perform a to b or b to a. If we perform a to b, then we have to put a negative sign at the end to make it b to a. If we change the path of the integration from a to b to b to a, we have to accommodate with sign a. So let's perform with a to b, and in this case we have the straight line. We have straight line with slope 1. This is 1, this is 2, x, y. So we want to perform from here to here, a to b. So here we have y is equal to x, straight line with the slope 1. So if we perform dy, so dy is equal to dx. And if we found dl, then it will become dx x plus dy y, and it turned out to be dx x plus dx y. We can change the variable x is equal to y. So in everywhere, then in function we have to replace y is equal to x, and it will become v dot dl will become so we change x to y, so we have x squared dx plus 2x into x plus 1, and everything is in x, and x is going from 1 to 2 dx. All right, now we have to perform the integration, so it will become x3 divided by 3 plus 2x square 2x3 3x3 and x 2x square x 2 x square by 2, and integration is from 1 to 2, so it will become x cube plus x square 1 to 2, and we have 4 no 8 2 cube is 8 minus 1 plus 4 minus 1, so 7 plus 3 is equal to 10. And if we find a closed loop integral, so if we are going from a to b and then coming from b to a, so we have 11 on path 1, and from if we are going from b to a, then we have to adjust the sign, so it is 1. So closed loop integral is not 1, so this is not a conservative field, or v is not a function expressing the conservative field or conservative force. So next video we will discuss the surface integral. See you in next video. Bye.